Okay. So I'm to record. So, okay. So welcome everybody. Today we are very happy to have Dr. Gwen Grinyer as a speaker. She obtained her PhD at the University of Guelph. Then she held a postdoctoral research fellowship at the National Superconducting Cyclotron Laboratory at Michigan State University. In 2010, she moved to France with the Marie Curie Research Award as a staff research scientist with the COA, that is the French Atomic Energy Commission. And she was stationed at the France National Heavy Ion Accelerator Facility at GANIL in Caen. And she was always a recipient of the ERC starting grant, so congratulations. And since 2017, she is assistant professor at the physics department in University of Regina. Today, she will talk about radioactivity at the limits of nuclear stability. So thank you very much, Gwen, for being here, and go ahead, thanks.
Okay, well, thank you very much for inviting me. I'm gonna talk about probably stuff that many of you don't think about, which are kind of radioactive nuclei, what happens when nuclei far away from stability. So those are the elements that we're kind of used to observing here on Earth. How do they decay? And I'm going to take you on a bit of a journey going from kind of the more common types of decay, nuclear beta decay, so you probably know about that. And then move towards more rare and more exotic decays where you actually have charged particle emissions through like beta delayed proton decays, and even something really exotic, ground state 2 proton radioactivity. So I'm going to start by talking about some of the questions that we have in this low energy nuclear physics regime. How do we study the various physics and problems that we want to study? And then how do we do it, which is building new detector systems and new facilities to enable us to learn more and more about nuclei far, far from stability. So this chart is probably the most important picture, and for every nuclear physicist, we basically plot what's called the chart of the nuclei, or the island of isotopes, where on the y-axis we plot proton number, on the x-axis the neutron number, and then every little square in this 2D grid is an isotope. And in black, you have all the stable isotopes. There's about 288 of them or so that are naturally occurring all throughout our universe. We know that there are these blue ones, which are radioactive. There's about 3,000 isotopes that we know about that are radioactive. But theoretically, we think that as many as 7,000 may exist, and we've just never been able to produce them here on Earth or study anything about them. What else you can see on this plot are these dashed lines, which corresponds to the sort of traditional shell structure that nuclei seem to exhibit near stability. And so we get these so-called magic numbers or shell gaps. And you also see these gray lines, which correspond to different processes, the RP process on the proton-rich side and the R process on the neutron-rich side, which are basically pathways that, nucleosynthesis pathways that can be accessed through explosive astrophysical scenarios. So I'll talk about that throughout the talk, but in the case of the R process, which is on the neutron-rich side, we actually think that all of the elements, nearly 50% of the elements heavier than iron, are actually produced through this R process pathway. And if I just go back one, you can see that the R process actually goes through a huge region of nuclei that we know nothing about. And once you populate all these different nuclei in a big explosion, they then will decay back to stability and produce all the elements around us. So we think nearly 50% of these heavy elements are produced this way. And if we just take everything we know, this is the relative abundance versus mass number for all the different isotopes, the stable isotopes. And if we take everything we know about nuclear structure near stability, and we just extrapolate that and assume the behavior sticks all the way to the neutron-rich regime, you see in the blue curve, we can't reproduce what we actually observe here. And it's a log scale, so we're off by quite a lot here. So what we have to do is modify the structure of nuclei near stability, and then extrapolate this sort of modified picture out to the neutron-rich regime to be able to kind of much better describe what we actually observe. And why that's important and what you need are nuclear structure inputs. So we need to know all these nuclei that we've never accessed before. We need to know what are their masses, what are their half-lives, how do they decay. This is essential for pinning down this our process pathway. Experimentally, though, we've never accessed them because they're extremely difficult to produce here on Earth. And so the ones that are most interesting to study are actually also the ones that are most difficult to access. And theoretically, the predictions have extremely large uncertainties in terms of what are the structure of these nuclei when we get way out there, and how do they decay and so on. On the right here shows you this famous LIGO event where they detected a binary neutron star merger. So basically 2 neutron stars colliding together. That was detected through the gravitational wave event, GW170817. And that's actually where we think all these heavy elements are being produced in the R process. This is one of the kind of key candidates for where these neutron-rich nuclei are being produced in our universe through neutron star collisions. And then when you talk about the neutron star itself, so neutron stars are of course predominantly made of neutrons, but out in the outer crust here, where it's cooler, you can actually have really neutron-rich radioactive nuclear species. And this is just one example of a mass measurement that was performed at the Isolde facility at CERN. And you can see the colored isotopes here. These are elements that we know something about. In white are all the unknown nuclei, and in red and blue here is kind of the limit where we think the limit may be based on theory. And in this one experiment, they showed that just through a simple mass measurement of zinc 82, they found that it was considerably less bound than what theory had thought. And as a result, it seems to be absent in neutron star crusts. And so this is extremely important because when you then take these 2 neutron stars and smash them together, it really depends on the structure of those, which is what's driving this R process. These are the sort of fuel for that process. And this is just to show you that even one measurement of a nuclear mass, for example, can make a big difference when you're trying to describe these very exotic structures in the universe. That's not the only place this occurs. We found in sort of this low energy nuclear physics experimentation that in black, these are the stable isotopes again. And we find all kinds of weird stuff when we go far from stability. So when we go out to extremely neutron-rich nuclei, we see modifications to shell structure that we know from our textbooks for stable nuclei. We see all kinds of weird structures like halos and clusters. And we can even find new forms of radioactivity like 2-proton decay that was only discovered in 2002 for the first time. It's a really delicate interplay between very, very weak binding. So nuclei on both sides at the very extremes are just barely held together through the nuclear force. And as a result, our theories can't always reliably predict where and when these changes will actually take place. So some of the big questions we have in subatomic physics, in sort of nuclear physics, low energy, what's the nature of the physics at the electroweak scale and beyond? How does the structure of nuclei emerge from the forces, and how are these elements formed? And so this is just taken from the Canadian Subatomic Long Range Plan. That's where my research comes in, kind of doing experiments on these most exotic nuclei to answer some of these bigger questions we have. Okay, so I'm going to start by close to stability. We move one off or whatever, and we're in a radioactive nucleus, and it's going to beta decay. Beta decay is, of course, one of the most common forms of radioactivity. And what all it is you start with a radioactive parent, and then it beta decays to a daughter, emitting either a electron for the case of beta minus decay or a positron for beta plus decay, and a neutrino. So for beta minus, it's the neutron in the parent converts to a proton in the daughter, and for beta plus, it's the inverse. The proton in the parent decays to the neutron in the daughter. On the right, you can see these are kind of the 3 fundamental quantities that we have access to in the lab. So we can measure the half-life of the parent. We can measure the energy difference between the parent and the daughter states, the so-called Q value. And we can also measure the branching ratios, which are when the parent decays, it can populate any number of excited states in the daughter. Those states can emit gamma radiation. And if we measure those gamma rays, we can determine the fractions by which all of these states are populated. So we can measure all of those experimentally. There's as well some conservation laws that we have to remember when studying beta decay. So just the language is that if you have orbital angular momentum L, which is equal to 0, and we call those allowed beta decay transitions, and any higher order L's are forbidden decays. They're not actually forbidden, they're just really super suppressed. So that's the orbital angular momentum L, the spin angular momentum S. If the neutrino and the positron or electron have spins that are anti-aligned in an S equals 0 configuration, we call those Fermi decays. And if they're parallel, then they're S equals 1 or so-called gamma of Teller decays. And so what I'm going to talk about today are mostly allowed transitions that are of the Fermi type. So L equals 0, S equals 0 transitions. When you go really far from stability, what actually happens is the Q value increases because you're getting way less or way further from stability, much less bound nuclei here. And so now the energy difference grows considerably from the parent, between the parent and daughter. So that part of the picture stays the same, but now you've got all of this space here that you could access higher order states in the daughter. And depending on where the next nucleus lies, all those states up here could actually be unbound with respect to proton emission. So if you have a proton daughter and you know its mass, you can calculate this so-called separation energy, which is just the energy above which protons cannot even remain bound in the nucleus anymore. And so when you beta decay into these states, they actually prefer to emit protons rather than a photon down to the ground state in this daughter here. And we call that beta delayed proton radioactivity. So it's a beta delay because you have to wait for the half-life of the beta parent. But as soon as you populate one of these states, the proton emission is immediate because it's unbound. So you get this beta delay followed by an immediate proton emission. And there's all kinds of delayed radioactivities. We've seen beta delayed 2 proton decay, beta delayed 3 proton decay, beta delayed alpha decay. There's all kinds of different stuff that can happen when you're much further from stability, as well 2 proton radioactivity that I'll come back to. Okay, so the measurement principle is then produce those nuclei, bring that radioactivity to your detector, measure the various particles and photons that come out, and then you can deduce everything you want to know about this particular decay scheme shown here. Okay, so this just gives you, this table just shows you that if you look at the different classifications, so that orbital angular momentum value, L equals 0s are the allowed, then you have high order L's here. And I just picked a couple of examples, but if you look at the half-life here, you can see there's a strong correlation between the half-life of the nucleus itself and the degree of forbiddenness or allowedness of that transition. This is a survey that was done on almost 4,000 different beta decays. And what we know is that 64% of all beta decay transitions we know about are of the allowed type. About 33% are forbidden, first forbidden. And then you just get a couple of really weird ones that are very high order forbidden. So just a few are known. And so you can see immediately from this table that you could almost use the half-life to classify the L value of that particular beta decay transition. And that's almost exactly what we do, except we make one modification that we take that half-life, we multiply it by something called F, which has the Q value built into it, and then divide by the branching ratio to that particular state we're looking at. And so rather than use the half-life to characterize the transition, we actually use what's called the FT value instead, but it's totally proportional to it. Okay, and the reason why we do that is if you write it in this way, then you can show that the FT value is just equal to some constants divided by the strength of the particular interaction, the weak interaction itself, divided by this sort of square of the matrix element between the initial parent and the final daughter state that's there. And if I plot those, this is a histogram of the number of known cases of all the allowed transitions and all the first forbiddens. And you can see here that in terms of FT, and this is a log scale, it's log FT plotted here. You can see that an allowed transition compared to a first forbidden transition is actually about 1,000 times faster. So the half-lives are much shorter for the allowed transitions compared to the first forbidden. And as well, if you look at this distribution for both the allowed and the first forbidden, this width of the distribution here is totally related to the nuclear structure or the wave functions of the states involved in the transition. So it's kind of this offset from the mean here for the allowed to the mean of the first forbidden, that many order of magnitude shift is the orbital angular momentum, but then the width of the distribution is actually related to the matrix elements because all of the green transitions have the same L value. And if I then zoom in on the y-axis, you have to go really far down in y to actually find the other cases. The second forbidden's, again, a huge suppression factor because it's much more forbidden. And then a big distribution related to the matrix element. And then there's just a couple of these third and fourth forbidden decays. But overall, these FT values range a lot. They range by 21 orders of magnitude or so, from the sort of fastest transition to the most hindered transition. And the other thing I wanted to show was if I take a small selection of the allowed transitions and I just focus on the 0+ to 0+ transitions, I get one grouping here, which basically there's 25 cases and they all give about the same FT value. And then there's 20 more cases that are totally different. They're heavily suppressed and they depend a lot on the structure on this matrix element here. And so what's interesting about these transitions are that in order to get the exact same FT value for all of these transitions, the only way that that could be true is that the strength has to be a constant and the matrix elements also have to be constant. Otherwise you get different FT values. So that's what we're going to dive into now. Why is that the case? So the first thing I need to tell you or remind you about is nuclear isospin. And it's been around for a long time, since the 30s. Heisenberg was the first to talk about the fact that protons and neutrons, if you take away the Coulomb part, are almost identical particles called the nucleon. And then you can just, from a nucleon, you can call a proton as a isospin down nucleon, and a neutron is an isospin up nucleon. And so you just treat the proton and neutron as isospin projections of this so-called nucleon. And then once you build a nucleus out of many nucleons, you can define the total isospin and isospin projection. And these are just vector quantities. So if all the neutrons were all aligned in isospin, then you would sum up all the individual plus a halves and so on. And so that's a vector sum that can take on any number from they're all anti-aligned to they're all fully aligned. And if you think about nuclear beta decay, all we do there is change a proton into a neutron or vice versa, which means we're just taking a spin down nucleon and changing it into a spin up nucleon or vice versa. And so all that is, the beta decay transition operator is then a simple ladder operator that changes the nucleon from one spin state to its other spin state, or isospin state, I should say. So that's, you can go and look up then what is the ladder operator for spin states in your quantum book, and you can find that for this special case of, it depends on the t value, but for the case of t = 1 decays, the matrix element actually evaluates to a constant, which is what we were looking for. And this formalism is exact to the extent that isospin's valid. So you don't actually need a nuclear theory to predict all the wave functions if you believe that isospin is an exact symmetry of the nuclear force. Okay, so going back to our FT, so I said that it's the constants divided by the matrix element, which for isospin, we can check that off. It's equal to 2 if we believe in isospin symmetry. The other question is about this GV, and is that it constant? Because if it was, then we could prove that all these FT values are constant. And for that one, we do believe it's constant through something called conserved vector current hypothesis. And it's done through direct analogy with electrodynamics. So if you look at, in electrodynamics, there's a conserved vector term or current, and that automatically leads to a universal coupling constant that you know and I know as the electric charge. And so you can measure this value, E, the charge on a proton or electron, to very high precision. And we know that it doesn't change if you take a free proton sitting over here, or you take that proton and you shove it into a nucleus, even though a lot of stuff is going on in the nucleus and there's all sorts of communication between nucleons, this particular value, the electric charge, never changes. And so the language is, it's because it's a universal coupling, and so it's never modified by the nuclear environment that it's sitting in. And if you compare the sort of structure of electrodynamics to the terms in the weak interaction, you find that most of the terms look identical. And so it was hypothesized then that the weak interaction probably also has a conserved vector current, and that leads to a universal coupling in the weak sector and through this GV. And we've measured this pretty precisely. And we've also determined that this does indeed seem to be constant, at least at the level in which that we can measure it. So experimentally, what we do is we just go and measure these FT values for many of these 0+ to 0+ transitions. And you can see in this latest survey from 2020, there's more than 200 or so independent measurements of all these various quantities, so half-lives, branches, Qs. And you can see here the FTs that we get seem to be remarkably constant. And even if you zoom in by a factor of 100, what you do see is we've measured these things to such incredibly high precision, and we do see relatively large differences on this scale, but the scale is only 2% here. And we understand fully now why there are small differences in the FT values. They're higher order effects. Probably the most important one that we need to worry about is this question, this isospin symmetry question. Can we really treat a neutron and a proton as identical? And we can't actually. There's a small asymmetry that causes this argument to be broken through charge-dependent forces. So we modify our isospin matrix element through a small correction term that we call delta C for Coulomb correction. Theorists can calculate this and determine this for us, so then we can just put it back in. But what you can see are the differences are on the order of 2%, and so that's about the size of the corrections. So these are pretty small corrections, 1 or 2%. There's other corrections as well, but this symmetry breaking correction is one of the most interesting ones. And when you put that in, what you see is you do get, for the corrected FT, remarkable agreement between all the various FTs for every single nucleus on this plot. So from carbon-10 all the way up to rubidium-74, there appears to be no difference whatsoever in the FT value. It's constant to an extremely high level of precision. It validates this assumption or hypothesis that the vector current is conserved. And this serves as a really strong constraint on theory or any new physics that may be out there. One of the things that our group's been working on is specifically looking for exotic couplings. So we are looking specifically for, could there be any scalar couplings in the weak interaction? We know there's vector, we know there's axial vector, those are the Fermi and the Gemma-Teller, but could there be scalars? And right now, we believe there aren't any, but we can actually use these FT values to determine a limit on by how much could there be small amounts of scalar in that interaction. And so if there were scalars present, then the FT would actually be modified. So rather than a constant, you'd get some other term that depends on W, which in this case is the decay energy. And that would actually cause these FT values to slightly deviate from a constant. There'd be some curvature here, specifically at low Z, where you would see this. And so what they do is they then fit a sort of term here. And of course, they get a value that's consistent with 0 because we believe there are no scalars, but we can set a limit on the strength of that scalar interaction. So previously the value is shown here. It's totally consistent with 0, of course. But what's most interesting in order to set limits on this are to look at these very light decays where you expect this curvature to be maximal if there were such a thing as scalars. And so we've been working for a number of years on half-life measurements, branching ratio measurements of these lighter decays, so carbon, oxygen, and neon. And I'm going to show you one example. which was a half-life of carbon-10 measurement that we performed at TRIUMF. And the goal there was to actually look at improving the precision, of course, that's goes without saying, but for the carbon half-life, if you look at previous measurements, these are scattered here from 1962 all the way up to present 2009. And you can see actually the last two most precise measurements actually disagreed with each other by about 2.5 standard deviations. So in our experiment, we really wanted to resolve that small discrepancy there. So if you're not familiar with TRIUMF ISAC, this is the radioactive beam facility at TRIUMF. Basically, we start with the TRIUMF main cyclotron, delivers a proton beam of up to 500 MeV energy, up to 100 microamp of current. The proton beam out of the cyclotron then bombards a production target. So that's where we produce our radioactive isotopes. Those isotopes enter an ion source, so then they become ionized, and then we can extract them in an electric field. So we pull them out, send them through a magnet. So charged particles in a magnet go in circles. And depending on the radius of the circular orbit through the mass separator, we can then choose the one we want, which corresponds to choosing the specific charge to mass ratio of the ion or molecule that we're interested in. This is a schematic of the facility. So the protons come in here, hit the target, and this is the mass separation here, and then it gets delivered up to the experiment. Carbon-10, this is what it looks like. It's a pretty simple decay. You start with a 0+ parent. It decays with a half-life of about 19 seconds down to only a couple of states in the boron-10 daughter, which is stable. This is that important isobaric analog state, the 0+ state that corresponds to the parent. And you get this strong kind of branching ratio of 98% to that. And in our experiment, what we decided to do was every time carbon decays, it emits the positrons. So we could just use a detector and count those. We can do that with extremely high efficiency. The problem, though, is that whenever you have radioactivity, you've got beta particles flying from all kinds of different impurities, potentially. And when you only count beta particles, you can't really discriminate which beta particle, whether it came from the nucleus that you're interested in studying, or it came from some other nucleus that was a contaminant in the beam. So it's a really great method in terms of efficiency, but it has no selectivity. So you have to really worry about contaminants. And the way our experiment works is we just bring in the beam, implant it for 20 seconds, build up a relatively hot sample of carbon, and then we move the tape over, this sort of band that you see traveling through. We move that over to this little guy here, which is the gas detector, and then we basically just observe the exponential decay radioactivity that comes out, and from that can determine the half-life. What you'll also notice, though, is almost 100% of the time, this beta decay also produces a 718 keV gamma ray. And so we could also use germanium detectors to measure exactly this transition here, and then from that look at as well the exponential decay of this 718 keV photon. The beautiful part about this experiment is that if you gate on 718, then there are no contaminants that also have photons of exactly that energy. The con is that it's a pretty low efficiency setup. This is an old experiment called the 8-pi spectrometer that we used for that measurement. The coolest thing about these measurements were that you can see we're actually only delivering ISAC beam for 20 seconds, and then for 500 seconds while we're counting the exponential decay, there's no beam at all. We turn it off. And so we thought, well, for 500 seconds, why don't we just send the beam over to the other setup and we'll do simultaneous operation. So we kind of ran 2 experiments in one, which was pretty interesting. This just shows you the decay curves that we saw for the 2 experiments. So on the top is the beta counting, and you can see there is a small amount of contaminant in there that we had to include in the fit. And you see as well for for this measurement, how many betas we have here. So 10 to the 6 or so in the first channel. And in the gamma counting, you see way less counts because the efficiency is lower. So you're way below 10 to the 6. But you also don't see the contaminant because now you've gated on that specific photons. These are really nice complementary techniques. And the end of the story was that we measured 1 cycle, took about 8 minutes. We did that 550 times over the course of 4 days. And from the two measurements, the beta and the gamma measurement, we got perfect agreement between the two different techniques and extremely high precision. So the 30 here only refers to these third and fourth decimal places. And it turned out that this measurement was the most precise half-life ever determined for carbon-10, as well the most precise half-life ever measured for any nucleus. And you can barely see the error bar here on this point. It's minuscule, but it's a new world record in terms of overall precision for a half-life. And so we were able to improve that, resolve this sort of discrepancy. And as a result, when we combine our number with a new mass measurement that took place in a different facility, we were able to actually set an even tighter limit on that scalar term that I showed you for the FT values for super loud Fermi beta decays. Okay, so what we're working on now, brand new, is we moved from carbon-10 over to oxygen-14. We ran this experiment as well at TRIUMF. So this is the beta picture, the same detector I just showed you. And we've now got a new measurement of the half-life of oxygen-14 to a statistical precision that's more or less comparable with the carbon-10. You can see this is one cycle, very pure. We don't see any impurities there. So we determine the half-life, from one fit, and then we do 168 cycles and we get consistent results across all of them. And our new measurement now is about 2 times more precise than the previous best measurement, and as well in really good agreement with all the other previous measurements of this quantity. So we're just putting the final touches on an article on that. And this was MSc thesis work of my student Shivani here at the U of R. In the future, we're going to work on the gamma ray side. And so those are new measurements that are coming up. And we've got a couple students here, Nasrin and Eric, who are working on those. One of the big differences, though, compared to the carbon-10 measurement, is that our gamma ray measurement is going to use a brand new spectrometer that replaces that older spectrometer. And this spectrometer is called Griffin. It's the new gamma ray spectrometer, much higher efficiency than our previous 8pi detector. And it's been already operational since 2015. So we're hoping to make a measurement to about the 0.03% level for oxygen. Okay, and for some of you that may be going to the WNPPC this week, as we have a postdoc, Dr. Kapoor here at the U of R, who's working on a branching ratio for neon 18. So if you're interested in this type of physics, there'll be a talk on Wednesday by Dr. Kapoor on a really interesting measurement where we've used a super high precision calibrated germanium detector that we've been working on for almost a decade to calibrate this and make sure we understand it. So I highly encourage you to go to that talk if you are at the WNPPC this week. Okay, so moving further away now, let's go from kind of normal beta decay to really exotic beta decay, but we have to move really far away from stability. So here are a region, just a small zoom in of the nuclear chart, and silicon-28 is a stable isotope of silicon, but I'm moving way over here to silicon-22, so taking away 6 neutrons from silicon-28. And silicon-22 is the most neutron deficient silicon isotope there is. It's located on this so-called proton drip line. It just means that there is no such thing as silicon-21, it's not bound. The isotope was only discovered in the late 80s at the GANIL facility in France, and first spectroscopy was performed in 1996. This is an example of the proton spectrum they measured in the 96 experiment. Production rate, 3 ions per minute, so that's not a lot, but it's still sufficient for spectroscopy. They determined that it's certainly a beta delayed proton emitter, has a really short half-life, 30 milliseconds or so. And even today, we've never actually measured the mass of this isotope because it's so difficult to get to. And if you look at the atomic mass evaluation, this AME, over the years, they keep guesstimating what they think the mass might be, and they get very different answers. And if rather than telling you what the mass is, I show you instead the 2 proton separation energy, And their latest one here says that it's strongly negative, meaning that silicon-22, there's also a 2-proton decay channel open, meaning rather than going from silicon and you beta decay to aluminum and then emit protons, you can actually, this nucleus is not even bound with respect to 2-proton emission. So just 2 protons basically fall out and get you to magnesium-20. And so that's one of the open questions. Can this nucleus do that? Is that even a possibility? There's a whole kind of interest behind ground state 2-proton radioactivity. It is so rare. Basically what happens is you start from your parent, and due to pairing effects in the nucleons themselves, you can't actually emit a proton and then emit another proton, so you can't go sequential. But from an energy perspective, it is possible to actually have a simultaneous 2-proton emission to go from the parent down to that magnesium-20 ground state. And it kind of looks a lot like alpha decay. You've got this 2-proton group just barely bound, and then it tunnels through this barrier that's keeping it in there, and then the 2 protons come out the other side. There's only 4 cases known. The most recent was from 2016, so we've added the 4th case very recently. And there's still a lot of debate over what's the nature of the decay. So we know the protons come out simultaneously, but are they emitted totally at random, or did they come out as some sort of correlated pair and then through Coulomb effects fly away once they're out of the nucleus? So we can understand that if we had lots of statistics, but we don't. We hope in the best cases measure a few of these per day, and in some cases much less than that. So going back to the silicon-22, I'll just show you some brief results from an experiment we performed at Michigan State in the US. So we were able to produce this nucleus with about 15 ions per second. We had other species in the beams, but they didn't emit any protons. They didn't bother us in any way. This is our proton spectrum, so considerably more statistics than the one I showed you from 1996. We identified 15 new transitions. We found this very important candidate here, which is the candidate for the beta delayed 2-proton emission. So not the ground state 2p decay, but this is the beta transition 2p. So much less rare than 2p. And we can measure the energies, we measure the branching ratios, and we even measured the half-life. So we got really good agreement. This is just the exponential decay curve of silicon-22. Really good agreement with the previous measurement. And from those FT values that I talked about, we can flip that around and deduce the Q value. And in this case, we showed experimentally that this value actually comes out to be positive. So the mass extrapolation was not correct. And so we've kind of shown that this nucleus cannot decay by this sort of extremely exotic 2p decay. So it seems to be a normal beta transition or normal beta delayed proton emitter. Okay, but those spectra that I showed are really, I mean, when you're using silicon detectors and measuring protons, you can learn a lot of stuff about the nucleus itself. And so one of the projects we're working on here in Regina is to build our own silicon detector for use at TRIUMF. So this is going to be a box of silicon detectors arranged in a cube. This just shows this is one detector, and then we have 6 of them on the 6 faces of the cube. And it's a new detector we're going to put inside of Griffin to study these beta delayed charged particle emissions. And the project's fully funded now through CFI and Innovation Saskatchewan. And it's a 2-year project, so we hope by the end of the year to actually have this ready to go for experiments at ISAC. And a lot of the work is led by 2 postdocs in our group here. So once we design it, build it, and test it here at the U of R, we're going to ship it off to TRIUMF for experiments with Griffin. This is a photo of the 6 detectors. They just arrived in October here at the U of R, so they're all ready to go. Their sides are only 6.4 centimeters, so the box itself, once you build a cube of this, easily fits, you know, in your hands or so. This is what the mechanical support structure looks like. So we're going to build a box and then just attach silicon detectors to the face of each box. You can see at the bottom, this is one silicon detector mounted. The really interesting thing about this is that we actually can print this in 3D using a 3D printer right here in our lab. So this whole structure here is one uniform piece of plastic printed out through a 3D printer, and then we're just going to attach our silicon detectors to it. And of course, like everybody, our work got interrupted and we started doing some other things. This is our postdoc, Miran. He started to design face shields when the pandemic kind of broke out. So we've been doing lots of things that are also not purely physics related. This is what it will look like in the Griffin beamline. So the cube is shown here. The beam comes in and basically stops somewhere in the middle, and then the protons get emitted, and we can measure those in the silicon detectors. And then this beamline itself actually sits at the center of Griffin. This is another CAD drawing. So now you've got the beamline there. The cube will sit inside this vacuum chamber in the middle, and then it's surrounded by all these germanium detectors, so we can study particle decays and photon emissions all at the same time. So we're starting to build this beamline in our on campus here. Hopefully by March we'll have it, and then by next year we'll bring it over and install it inside Griffin. All right, so with that, I wanted to then, to make sure I don't run out of time, I wanted to then switch gears a little bit to talk about silicon detectors are great. And I mean, we are investing the time and effort to build a silicon array. So they are fantastic, but they can't do everything. And so one of the things they can't do is search for super, super rare decay modes like the 2-proton radioactivity that I showed you. So in that case, what you need to do, rather than a silicon detector, is use a gaseous detector, and specifically use a time projection chamber. So TPCs are extremely useful if you want to study rare decays. Things like beta 3P, where the branching ratios are tiny, you expect only a couple of counts. With a TPC, you basically take a photograph or an image of the event, so you can identify that this thing has occurred even with one picture. That's very different than a silicon histogram. If you have one count in a histogram, you can never say anything. But if you have a full photograph of what happened, then only one event is enough. And you can see here, this is a device called the optical TPC, where they've measured like the beam comes in, stops, and then emits 2 protons. So you see that directly. This is the beam coming in and emitting then 3 alpha particles. And so from the length of the tracks, from the brightness of the tracks, you can completely identify what has actually occurred in there. So they're super powerful detector. How it works, it's pretty simple. It's a gas-filled box. The beam comes in and the particles fly out. And as they do so, they ionize the gas of the TPC itself. You surround that in an electric field, and all those electrons you produce from the ionization then drift, and they come down to a pad plane here that we segment into little pixels. And so it's exactly like a digital camera. The more pixels you have, the higher resolution your image is going to be. So our detector has 16,000 of these pixels, fully digital electronics for every pad. And this was, before we started, totally unheard of in our field to have so many channels of digital electronics in a nuclear physics experiment. Just never occurred. So we had to do a lot of work on electronics, the DAC, how do you actually connect all these signals to the, from the pad plane to the DAC, and so on and so on. It was a huge development that took several years. I just want to show a picture of our prototype to give you a flavor for how dense this is. This is the backside of it. You can see it's only 6.4 by 12.8 centimeters in dimension. So this is the size of your phone, basically. And each of these pins corresponds to one of the pixels on the other side. And there's 2,000 of these pins there. The final detector was then 8 times bigger for the 16,000 channels. But you can see each pin is 2 millimeters apart from each other. So we have 2,000 channels we're reading out in something the size of your cell phone. The project to build the whole detector, as I said, took many years. It was the focus of an ERC grant. And we went from building that prototype all the way to first physics experiments. And it only just ended recently. We ran 2 experiments in 2019, and we have 3 more scheduled this year, and more to come as well. This is what it looks like in real life. So the detectors here, this is about the size of a person. So if you were to stand here, you'd be about that tall. It's not a super big detector, but it's extremely high density signals coming out. There's 16,000 of these channels. So we have to get all that over to our electronics chassis over here to read them all out. So anyways, it's a really complex project. I could talk about this all day, but I'm just gonna skip right now to tell you that it works and we're already running experiments. And I wanted to show you specifically this experiment where we were looking in nickel 54 for possible proton emission P1 and P2 here from a highly excited state in nickel 54, which is itself radioactive. So it's complicated because you have to produce the radioactive nickel 54. You have to hope that sometimes when you produce it, it's in this excited state. It's very rare to do that. 0.4% of the time it's in that state. You then have to bring that over to your experiment, the TPC, stick it in there, watch the protons come out, and do all of that from production to proton measurements in only a few hundred milliseconds. Because of course, if you don't get it to the detector before then there's no nickel 54 left to actually study. So this was an experiment performed at GANIL. It was the first time we ever used our TPC for such a measurement. And I've got some movies to show you. So this left movie shows you what an artist's rendition of what it looks like. So this is our pad plane and the beam enters from here. So that's your nickel ion coming through, and this is the electrons that it's producing there. It's all throughout its trajectory, and it comes to a stop at some point in the middle. And then after a while, the half-life, it then emits a proton, and you can see as well the electrons from the proton. They then drift down in that electric field, and the electrons arrive at this pixelated pad plane, and then we can deduce everything we need from the charge collected at each position. We get the angles. We also know the time difference between the nickel signal and the proton signal, so that tells us about the lifetime of the state. The movie on the right is the same, but these are real data now. This is not an artist's rendition, so it's the same kind of thing where the beam comes in blue, the proton will decay, and there's a time difference between the two. The time delay is related to the lifetime. So from the track length, we plot down here in this plot, and from the lifetime or the time difference, we plot here in the right plot. And I'm just gonna run through, this is one event, so there's one count in each of these spectra, but I'll run through many events from our actual experiment in 2019. So you can see how on an event by event basis, we get all that information and can plot the track lengths, which are related to the proton energies, and as well that time difference, which is then related to the half-life of that state. Okay, and just to highlight too, it isn't a simulation. These are real events from our experiment. And I just want to thank my colleague in Bordeaux who did all these amazing videos, and the work of this experiment we just submitted to Nature, Nature Communications late December. So hopefully these will be published results really, really soon. On the horizon, we're actually going back to GANIL in 2021. Well, not us because we can't travel, but we're going to be there remotely doing experiment on the 2-proton radioactivity of zinc 54. Again, this is this very rare case, only a few are known, but what you get out of the TPC are these angles and the energies. You get all this amazing information that you just don't get with other methods like silicon detectors. The previous experiment on zinc 54 in a TPC, they only had 7 total events, and we're hoping now in May that we're gonna see 8 events per day, and we're gonna run for 15 days. So we should have something like 120 or so total events, so almost 10 times more than the previous statistics. The detector is so exciting. There's lots of stuff that people want to do with it. And right now there's a lot of future plans to bring this detector from France to perform experiments at other facilities around the world, like RIKEN in Japan, bring it to Isolde at CERN. But where I come in, I'm leading the group to bring this detector over here to ISAC. at TRIUMF to study both in-beam reactions, but also various decay experiments like I showed you. There's an endorsed LOI to bring it. We have one experiment already approved, and we're kind of thinking after our experiments that we already have planned at GANIL, we could possibly bring this over, you know, in 2022 or later, depending on how everything goes. So there's really lots of really cool stuff to come, and I hope that those pictures kind of convince you that this is a really, really interesting detector and an amazing way to view nuclear radioactivity at the limits. Okay, so with that, I'm just going to conclude. One of the most exciting things for us is this, as nuclear physicists, is of course, these new detectors are one thing, and new ways to measure radioactivity is so important. But of course, the flip side is we need facilities that can produce beams and send them to us. We need to have at least a minimum threshold of so many events per second to be able to see these things in our amazing detectors. And so one of the outlooks for the future, specifically for my research here at the U of R, is the ISAC facility where we presently do experiments, but as well the future facility Ariel. Ariel is going to be able to produce all kinds of neutron-rich species that we basically are not able to reach with present-day ISAC facility. This new facility Ariel should triple their isotope beam delivery capacity. It'll run in parallel with ISAC, so we're just going to have more beam, more hours to be able to do our experiments. And those beams from Ariel will be sent to our existing experimental area where we have Griffin and where we can bring our TPC and things like that. So it's really exciting. First beams could be, you know, as early as 2025 or so. So that's really something to look forward to in the future. Okay, so with that, I hope I convinced you that all these unobserved nuclei really hold some of the answers to our big questions. We're doing experiments with rare isotopes using both new techniques and really state-of-the-art detection systems, going from kind of normal beta decay all the way out to really exotic forms of radioactivity. And this has to be coupled, you know, the technology of the detector side has to be coupled with the more powerful accelerators and production methods like at Ariel or even the facility for rare isotope beams, which is another new facility coming online in the US. We're doing experiments today that we literally never dreamed of 20 years ago. There's so much discovery potential, and it's really an exciting time for rare isotope research. And so with that, I want to thank you so much for the opportunity to speak today, and thanks to all of our funding partners for all these different projects that I showed you. Thank you.
Thank you very much for the nice talk, the great talk. So I see already some hands up. Chris, go ahead.
So thanks very much. I really enjoyed that. Can you go back to slide 48? Where you show the your double-sided silicon detector in amongst the gamma array. Yeah. So what is the experimental signature you're looking for in the silicon detector?
So it depends. I guess one of the experiments could be, for example, we're going to look at beta delayed proton radioactivity. So then we'll see in the silicon detector the protons come out, but then after that, you could also, from a proton decay, populate excited states in the daughter. So you'll also get gamma rays coming out at the same time. And we can then use the silicon detector to record the protons and the gammas, or the germanium detectors to record the gamma rays.
Okay, got it. Thank you.
Another thing that I wanted to mention too was if you have really exotic radioactivities like beta 2p, the silicon should see both of those protons at the same time. So you record a coincidence signal between two protons, and then you'll know that that decay was beta 2p as opposed to beta 1p. So you can actually measure multiplicity as well. And that selects out for you those really rare exotic branches, not the normal one proton decays.
Thank you.
Pierre, you're next.
Hello, thank you for the great talk. Questions about the different facilities. So you are hinting that they are complementary. So what makes them different?
You mean the production facilities?
Yes, so GANIL, Isaac, Isolde. Why obviously they seem to, since you want to move your great TPCs left and right, it means that they cannot deliver identical beams or even identical isotopes. Is it true?
They in a lot of cases they do, but there's also the complementary comes into the fact that each facility kind of has its own special regime where they've already demonstrated really exciting beams. GANIL, if you want to study a noble gas, then GANIL is really the place to go. They have intensities that are unmatched around the world if you want to study noble gas radioactive isotopes. Whereas, TRIUMF seems to be a leader in really, really short-lived radioactive isotopes. And Isolde as well has its, benefits, pros and cons. And yeah, you figure out what physics you want to study, what beam do you actually need, and then you can go and look at the various facilities to see what rates they can provide. And then you go to the one that has the highest rates. And that's why we like to move it around, because each of these facilities kind of has their own niche of where they really are, they dominate or they're totally competitive for one specific beam over another one.
Thank you.
So Sakshi, you're next. I think I must pronounce his name.
Hi, can you hear
I don't know. Yeah. Yes. Now,
Hi.
yes.
Yeah. That was a great talk. It was really interesting to learn more about radioactive decay. But my question is, the fans that were present in the panoramic picture, I was wondering what they were for.
Sorry, let me just pull that up. Of the TPC, you mean?
Mm-hmm.
Oh, yes. This is our low-key fan system to cool down our preamps. So
That's great.
We have electronics here, and you can see there's little fans here. So this is high tech. We have very high power fans for the electronics of the TPC, but we also added a silicon detector. So we just stuck on an extra preamp back here, and that got really hot, and we had no fans because we didn't foresee that. So then we just added these on the ground floor to cool that off. So, but unfortunately, yeah, we should have taken the picture before the fans went in, so it didn't look so low key.
Reminds me of what we needed to do with the snow electronics.
Yeah, so.
Thank you.
Serge, you are next.
Yeah, thank you. Thank you, Silvia. Thank you very much for the very interesting talk. You actually cover a lot of interesting and typically omitted decays and omitted activities that we are looking for very rare nuclear decays. But could you please come back to the slide number 48, where you're discussing about this cube with silicon like pixelizer detector?
Sorry, this one here?
Yeah, this one. I'm actually curious, since you 3D printed this support for this 6 different plate, and it's like a plastic means, and after that you connect it to the metallic beam guide, let's say, and also like a holder of this detector. But I'm curious how you will be able to cool these detectors, because when it will be irradiated, probably this detector will be warmed up. But plastic is not the good thermoconductor.
Yeah, so you actually hit on a point that I didn't bother to tell you about. That is that, first of all, these double-sided silicon strip detectors here, they're high purity silicon, so they don't actually have to be cooled to be used. So we can use them at room temperature. So there's no active cooling at all in there. And then on top as well, like if you look at the frame, there's kind of this slit here. So that's where the beam's going to go right through that gap to get into the middle of the chamber. The detectors, it's not a perfect cube, of course. You have to open it a little bit to get this beam in there. And so we know roughly the beam size that ISAC typically delivers. And then we made that hole much bigger to make sure that the beam is not going to hit the frame. But yeah, we don't have any sort of active cooling of those strip detectors. So as long as the beam doesn't hit them, we should be okay.
So it means like a current also like a beam is not enough in order to warm up your detectors. It will detect also like a high intensity particle.
This is so exotic stuff. If we get like 10 ions per second, that would be fantastic, but there's no current that can be measured from a couple of ions per second coming down a beam.
I see. I see. Yeah. Thank you very much.
Yeah, you're welcome.
Shimon?
Okay, I think it'll be a quick one. First of all, a fantastic talk. Thank you so much. A tremendous amount of work. And I think Serge has already taken my most of my questions. So maybe a quick one then. What is the holder, the 3D printed holder made of? I've been wondering about any interference with the beam.
You mean just what material?
Just a typical polymer?
Oh, I don't remember the acronym, but we buy it off Amazon. It's straightforward stuff for 3D printers called PLA filament. And I don't remember now what the PLA actually stands for, but it's a solid plastic, and then that's about it. There's nothing really special to it.
Okay. Well, that's interesting. That's
yeah. I mean, it's pretty rigid too. Like you could not easily in this setup. You can't really break it with your hands. You need a pretty strong mechanical force to actually break it. It's pretty sturdy.
Very interesting. Thank you.
You're welcome.
I don't see any other hands up beside the one that were already up before. Are there any other questions or comments? If not, I would like to thank you, Gwen, again. Very nice talk.
Thank you so much.
Thank you very much for being here today, virtually.